You may have read recently about New Orleans, which has a very large number of COVID-19 cases. And if you're also paying attention to the news, you know that New York City is now the global epicenter of the coronavirus epidemic. Why is this happening? You're watching 11 Levels. Note this is not based on the video series 5 Levels by Wired.com. Well, okay, maybe just a little bit. So we go back to this article. There is some speculation among medical experts that the event of Mardi Gras may have accelerated the crisis, and it's really about the unfortunate timing of the event and the characteristics of it. So if you just ask how many people attend Mardi Gras, then it just gives you the number. And this is a very large number, and these people are really packed together. I've actually been to Mardi Gras, and it's really like this. It's really, you feel like you're in a subway car, if you will. Speaking of which, the New York City subway system hosts 4.3 million people every day. So whether it's Mardi Gras or not, there are 4.3 million people who are packed together, many of whom look like they're packed together in Mardi Gras, but they don't seem to have the same exuberance about doing so. So this is really a situation which can be very, very dangerous if there is a disease, because we know that COVID-19 is spread through breathing and so forth, and proximity to other people. So now I want to talk about this SIR model. This is a minimal model of epidemics that has three populations: a susceptible population, an infectious population, and a recovered population. And somehow the color scheme here is different from the color scheme that you see here. This is the susceptible population, this is the infectious population, and this is the recovered population. Okay, so I want to give a shout out to a video by Trevor Bassett, and he talked about the math of epidemics, and this is a very nice description that is more qualitative, I would say, than what I'm going to be describing. So again, you can see, so here now the color scheme is correct. S is the susceptible population. I is shown in green is the infected population. R is the recovered. And the only thing that, of course, he pointed out in the comments, but in my opinion really shows that he was just doing it himself. He was not just copying and pasting from somewhere else, is that this R should really be B. So the point is that there are two parameters, A and B, in this model, and they determine the entire dynamics of what goes on. So, well, also there's, I should say that the initial population, which in this case is 500, is also a parameter, which goes into something that is called R naught in epidemiology, which is a number that tells you whether infections lead to exponential growth or exponential decay. So if this R number, R naught, is greater than 1, then you have exponential growth, and if it's less than 1, then you have exponential decay. So I'm going to go into this in more detail. So there are three variables, S, I, and R, and the rate of change of susceptible is given by minus A times the S times I, and the rate of change for I is A times S times I minus BI, and then the RDT is equal to B times I. So these are three equations, and You can also write them so that they have explicit time dependence. So these S is really a function of time, I is a function of time, and R is a function of time. The coefficients A and B are assumed in this model, in this particular model, to be constant. And so there are going to be some initial conditions. So the idea is that initially you have some initial population of, let's say, 500 people in a community, and then one of those people is infected. And then initially there's nobody who is recovered because nobody was, this person has not recovered initially. So this is the equations. And what I want to point out here is that the class of coupled differential equations this is basically nonlinear, because you have a variable times another variable on the right-hand side here and over here. So that makes this problem a little bit more challenging to solve, but it's not. It's actually numerically quite straightforward to solve. It's just that in terms of writing down an answer analytically, it's more complicated. It's harder to do that. So this is a coupled set of nonlinear first-order differential equations. What we can do, though, is we can linearize this set of equations for small times. And trust me, we want to think about small times, because the large time limit of this is one in which a large fraction of the population is infected. And that's a very scary prospect to think about. So what we want to do, and we're actually still in the linear regime right now, so this is going to be a good approximation, or at least at the time that I'm recording this. So what do we do? We're going to take the first equation, and we're going to make an assumption that S is equal to S naught. Okay, so what this is saying is that basically then the number of susceptible people is roughly constant. And so now I've gotten rid of that nonlinear term in this equation. Then I can do the same thing on the second line. I can replace S by S naught. And so I have the I dt is equal to A S naught I minus BI, which I can factor, and I can call this R. So R would be A S naught minus B. And then the third one is going to be, it was always a linear equation. So we can now focus on the middle equation here, which is telling us at what rate people are getting infected. And so this equation is now much simpler. It says the I dt is equal to R times I, which we can solve as I of t is equal to e to the R times t times I0. So this is something that you would learn in first year calculus. And remember, R is a parameter which is basically given by A S naught minus B. So that's what R is. It just comes from this equation here. So R is the parameter which is going to tell us whether we have exponential growth or exponential decay. And that makes all the difference in terms of an epidemic. So if this lowercase r is greater than 0, then we're going to have exponential growth. And there's another way of writing this, which is to say that if lowercase r is, which is this, is greater than 0, then that means that A S naught is greater than B, or A S naught over B is greater than 1. And so this is what is known as capital R0. And so when this parameter is greater than 1, then we have exponential growth. And when capital R is less than 1, we have exponential decay. So the point is that these parameters, well, S naught is really the population of your community, whatever that you're considering. A is a parameter which is influenced by things like social distancing, or whether you are packed into a subway car, or whether you once a year at the unfortunate time happen to be in a crowd on Bourbon Street. These are going to be parameters which will be larger or smaller in your community. And then B is going to be something that is really biological, and it's related to your ability to recover from this disease. So again, to summarize, that when little r is greater than 0, or capital R naught is greater than 1, you're going to have exponential growth in the number of infected people. And if it's less than 1, then it's going to decay to 0. And it all comes from this rather simple equation. And it's really the exponent of this which is going to determine what happens. And the value of the exponent is going to depend on the particulars of community, for example. All right, so now I want to transition to a Mathematica model, which is a mathematical model of the SIR. And this is for anybody who has Mathematica and wants to play with the equations to get more familiar with them. I've made this available on my website, and you can just go to this link here. So what I've done is put in an initial condition, S naught, which is the initial population. And then I wrote down the set of 3 coupled ODEs, ordinary differential equations. So this is the time derivative of the susceptible population, which is minus A times S times I. I is the infected population. The time rate of change I prime is equal to A SI minus B times I, and R prime is equal to B times I. So these are the 3 sets of ODEs, and they're nonlinear and they're coupled. And the initial conditions are that at t equals to 0, the initial population is S0, which is 500. The initial number of infected persons is 1, and the initial number of recovered people is 0. So to solve this, I just say ND solve, and then I give the variables and then the time range over which I would like to solve them. So I don't have to worry about doing creating a solution. And then I'm going to calculate this quantity R naught, which is A S naught over B. This is the capital R that people use in epidemiology. And then I'm going to create this. It's going to dynamically update. And then I'm going to plot 3 things. I'm going to plot the number of susceptible, infected, and recovered people as a function of time on a linear scale, and then I'm going to plot it on a log scale, and then I'm going to do a parametric plot of the rate of change of infected people versus infected people. And so when I hit Shift Enter, it's going to create this. Now this is a R0 of 1, and so I'm going to use these parameters A and B to represent these are sort of parameters that depend on, for example, where you live and your biology. So I'm going to change the biology to be 0.1, and then I'm going to increase A. And pretty soon you get to a point where it looks like what you see on Wikipedia. susceptible population is going down, number of infected people is going up, and there's this crossing point here, which is where the number of infected people it reaches a maximum. And then this is what it looks like on a log scale. So this is population is now shown in logarithmic units, and then the horizontal axis is still time measured in days. Now, what Henry Reich and others were emphasizing is that if you really want to know when things are changing, so the point is that at small times we can analyze this as an exponential increase of the number of infected people. If we really get to this point and nobody has done anything, this is a really, really bad situation, because what it means is that most of the population have gotten infected. And whether that takes a few weeks, a few months, or a year, the same number of people are going to die. So that's, of course, things could change in the sense that there could be a vaccine and so forth. But if you're just slowing things down, and you're slowing them on time scale of less than or equal to a year, then really you're not changing how many people are ultimately going to be severely affected by the epidemic. And so what Henry Reich and others were pointing out is that if you plot di dt versus I, then you get a curve which is going to be, this is actually a log plot of di dt versus I. Then what you would see is that it would be a straight line, and it only really starts to turn over once you do something, when society makes a decision to enforce social distancing, for example, or if there's a cure, something that's going to change these parameters. So the B parameter is really a function of your biology, and unless you're given something, like everybody is suddenly given something that would, like a vaccine, for example, this B would or cure, basically, this number is not really going to change. And then this is the number that really is influenced by our behavior. So if you suddenly make a change here, then you'll see it in this curve. And the only difference is exactly where in the curve you see it, whether you see it when a large number of people are infected or a small number of people are infected. At some point, there is a change in the shape of the curve. So there, I've made it log, and this is log base 10. And note that I am, in this plot, I'm only showing I'm only showing up until the first 15 days. So if I make a change like this, for example, I make this 25 days, then you can see that it starts to go down from day 25, because at this point now the slope of the number of infected people is negative, and so this is all going to go off this axis. So again, there is a point where this thing will naturally turn over, but that's because you're essentially depleting the population of susceptible people. And that's really what we want to avoid, because 1% of the world's population is still a very large number of people. So there you have it. I went through all of this really so that I could have a better understanding of what's happening to to all of us. And for me as a physicist, I want to have the simplest model that explains almost everything, and that is the elegance of this SIR model. And so I think if you're mathematically inclined or you have if you're comfortable with differential equations, then understanding this model, I think, will help with your intuition as you read through all the statistics every day and try to understand what's going on and what the impact of various social distancing and other actions that are being required by society and by communities around the world. And hopefully this will help you understand what's going on, and when you see predictions, for example, about when we'll be recovered and so forth, if you understand the parameters of the model, you can evaluate for yourself whether these predictions make sense or whether they're consistent with the simple modeling that you can do.